Good morning. Last class we discussed deflection, slope and elastic curve with respect to a simply supported beam, and also we derived expression for differential equation for deflected beam, and that the differential equation can also be called as Euler's-Bernoulli's differential equation for flexure. The differential equation which we derived is EA into d square y by dx square is equal to m. Now, let us discuss a method how to determine a slope and deflection by using a differential equation for deflected beam. Next is Macaulay's method. Method of slope and deflection. So, to determine slope and deflection we have different methods, and those different methods you are going to learn in the next semester in analysis of determinate structure. Here in strength of material you are going to learn how to determine slope and deflection of a loaded beam by using a Macaulay's method or double integration method. So, Macaulay's method can also be called as double integration method. So, the famous mathematician Macaulay who invented this method, hence the name Macaulay's method. Macaulay's method is one of the simplest method of determining slope and deflection. Here we use the differential equation for deflected beam, namely differential equation for deflected beam namely EI into d square y by dx square is equal to m. If we integrate this equation, suppose let us call this as equation 1. If you integrate this differential equation for deflected beam successively twice with respect to x, we get two more equations. So, if you integrate this equation once, we will get the equation in terms of dy by dx, and dy by dx is nothing but slope. Yesterday we had discussed while deriving expression for the same. Slope at any point of the curve is equal to dy by dx. If you integrate this equation 1 with respect to x, we will get one equation in terms of dy by dx, that is equation slope. Suppose again if you integrate this equation, the integrated equation again once, you will get one more equation in terms of y. So, dy by the equation consisting of dy by dx is known as slope equation, and the equation which consists of y is known as deflection equation. In order to understand this Macaulay's method, let us consider a simply supported beam subjected to 2 point loads. Consider a simply supported beam of span L subjected to 2 point loads, say W1 and W2 at a distance say A1 from one end and A2 again from the left hand side. The salient points are A, B, C, D. Let RA and RB be the support reactions, and we are well versed with the concept that now we can, with this loading condition, we can easily determine support reactions at A and B. Here, to understand the Macaulay's method, we have considered the differential equation reflected beam, and also we know that if you integrate equation 1 successively twice with respect to x, we get two more equations. One equation containing dy by dx, it is slope. The other equation contains y, it is called as deflection equation. So, to understand this, so we consider this simply supported beam subjected to point loads. Let RA and RB be the support reaction. In Macaulay's method, we select the section in the last segment. So, this is the section, and this section lies or acts at a distance or lies at a distance of x from the left hand side. So, left hand side we proceed, if you proceed from left hand side to right hand side, and this the starting point we call it as origin, and this is the destination or end. So, x this section lies at a distance of x from the origin A, means here x varies from 0 to L. We have taken the distance of this section from A, so it may be A1 or it may be A2 or it may be a L. So, x vary, the range of x is 0 to L. So, in differential equation for deflected beam, term EI is known as flexural rigidity, E is Young's modulus, I is moment of inertia, and M is the bending moment, and this bending moment we are going to consider about the section. M is the bending moment about the section by considering forces towards the origin. We selected origin as A and we have selected section in the last segment. There are three segments here, 1, 2 and 3. So, M is the bending moment about the section. So, equation 1 takes the form that is, so write equation 1 left hand side as it is, EI into d square y by dx square is equal to, M is bending moment about the section, here. See here to the left of the section, while writing expression for bending moment, to calculate bending moment at a point, the algebraic sum of moment of all the forces to the left of the point or to the right of the point gives us bending moment about that point. Here the same concept where we use here, but only thing is we consider all the forces acting towards the origin. There, to calculate bending moment at a point, we consider forces acting to the left of the point or to the right of the point. Whichever the side is easier to us, that side we used to consider. But here compulsorily we have to consider forces acting to the left or towards the origin to write expression about the section, to write expression for the bending moment about the section. So, bending moment about the section by considering forces to the towards the origin or left side is equal to Same sign conventions are valid here also. What we do, if we consider forces to the left of the point, we consider clockwise moment as positive and anti-clockwise moment as negative. The same sign conventions we use here also. To the left of the point there are three forces here. So this reaction will create a clockwise moment about section, and these two point loads will create the anti-clockwise moment about section. Now, so RA will create clockwise moment about section. RA, the distance, perpendicular distance is x, RA into x. So this is the moment, bending moment due to RA about point x or about section x. Next, this W1 will create anti-clockwise moment. When we treat clockwise positive to the left hand side, automatically anti-clockwise will be negative, minus W1 into perpendicular distance, this distance from here to here, this is the perpendicular distance for this W1 up to this section. So for that we know distance from the origin to section, it is x. We want this distance, we know this distance, we want this distance, means x minus a1, that gives you the perpendicular distance between the here, x minus this much. So W1 into x minus a1 is the perpendicular distance for W1 up to this section. Next, let us consider W. This W2 is also creating a anti-clockwise moment about section, minus W into perpendicular distance between section and this point load, this distance. Again for that we know x and we know distance from origin to D, it is A2. So x minus A2, x minus A2, that's all. That is, we call it as equation 2. What we did here is, we considered the differential equation for deflected beam, and here again we retained the left hand side as it is, Ea into d square by dx square. Right hand side is bending moment about section. For that we have taken section here and we consider the forces to the left of the section, means towards the origin, and here we have considered all the three forces to write expression for bending moment. Ra into x clockwise positive, W1 into x minus a1, this anti-clockwise, again minus W2 into x minus a2 anti-clockwise. Now if we integrate equation 2 successively twice, if we integrate equation 2 successively twice with respect to x, we get that is integration of equation 2. Equation 2, it is Ei into dy by dx, integration of d square by dx square, that is equal to Ra into x square by 2. Again minus W1 into x minus a1 whole square divided by 2. Next, minus W2 into x minus a2 whole square by 2 plus C1, call this as equation 3. So integrated equation gives us equation 3. In equation 3 you can see the term. So this term containing dy by dx means So this is the equation for slope along with this flexural rigidity. Next, further integration of equation 3 gives, that is integration of equation 3 again EI into, so integration of dy by dx is y, that is equal to RA into x square by 2, RA into x square by 2 means x cube by 6, integration of x square by 2 x cube by 6 minus w into minus w1 into x minus a1, earlier it was square, it was cube by 6, again integration of third term minus w2 into x minus a2 whole cube by 6 plus c1 we already written, it is c1 into x plus c2, introduce another constant. So this is equation 4. See here, if you integrate equation 3 again with respect to x, we will get this term ei into y into RA into x cube by 6 like that with constant, another additional constant. So this equation containing the term y, and this is along with E into I, flexural rigidity. So this equation is known as slope deflection equation. So this is slope equation, and this is deflection equation. You can see here we already defined that from the figure here x varies from zero to L. We have selected section in the last segment such that x varies from 0 to L, and based on that concept we have written the expression for bending moment about section x by considering forces to left hand side. We got equation 2, then if you integrate equation 2 successfully twice with respect to x, we got 2 more equations, and this is the slope equation containing the added constant c1, and further integration we got equation 4, and this equation consisting of 2 more constants, 1 more constant again. Earlier we introduced 1 constant, further 1 more constant we introduced here, it is c1 and c2. So in equation 4, 3 and 4 you can see c1 and c2. The c1 and c2 are called as c1 and in the above equation. In the above equations, C1 and C2 are called as integration constants. And these constants can be obtained by applying boundary conditions. So C1 and C2 can be calculated by applying the boundary conditions. If you calculate C1 and C2 in equations 3 and 4, we can substitute C1 and C2, then already we defined x varies from 0 to L. Knowing C1 and C2, then equation 3 and equation 4 will be ready for yielding slope and deflection wherever we want. Say for example, after substituting for C1 and C2 in equations 3 and 4, if you substitute value of x means x varies from 0 to L. Wherever you want, you can substitute. If you substitute x is equal to 0, then it is will get some value. If you substitute x is equal to a1, will get value. If you substitute x is equal to a2, will get value. Similarly, the same way we get the deflection by substituting x values in equation 4. So boundary conditions are important here. So this is about the Macaulay's method. So regarding boundary condition, let us discuss in detail. So once we know the boundary conditions, along with this Macaulay's method, knowing the differential equation for deflected beam, we can easily solve any type of numerical problem to find slope and deflection at any given point of the beam or at any combination of loadings. Now, boundary conditions. Let us consider first one. Let us consider simply supported beam subjected to a loading. For a simply supported beam subjected to loading condition, yesterday already we discussed that it is say W1, W2 or any combination of load, that is say W per meter. Here the deflection say point B, A and B, this is A and B. The beam will deflect like this after the development of bending moment. So when beam deflect like this, we can write value, this is y, and we can also draw tangent at the ends. So this is called as rotation. We can also draw tangent here horizontally. So this is the rotation theta A and this is theta B. So L. So we select section here at x. X is equal to this one. X varies from 0 to L. Now we have to create the boundary condition here. It is known already to us that. So deflection is nothing but lateral displacement. Lateral displacement. So here deflection is 0 at point A and deflection is 0 at point B. Again, if you draw tangent to the deflected curve, we can draw tangent here and measure the rotation. The slope is rotation is clockwise, whereas here rotation is anti-clockwise. So that we can measure slope both at point A and B after drawing the tangent. Of course, if you draw tangent here, it is a straight line. It is 0. We have slope here, we have slope here. Slope may be maximum at either of the two supports, depends upon the the position of the load, the maximum load. If the load acting is more towards B, rotation is more at B. If the load acting is more towards A, rotation is more towards A. Depending upon the loading combination, the rotation can be measured. The same way, deflection again depends upon the majority of the loading point of application, the deflection, maximum deflection occurs. It may occurs at the center, it may slightly deviate to the left or to the right, that again depends upon the point of application of load. You can see very simple, here deflection is 0, deflection is nothing but lateral displacement. Deflection is 0 at A, deflection is also 0 at B. Then what is x here? Already we stated that x, we select a section in the last segment x, it is the distance x from A to the section, so that x varies from 0 to L. In the differential equation are like, if x is equal to 0, then deflection is 0. Again, if x is equal to L, again deflection is 0. That is one two boundary conditions. Two more boundary condition we can invent here, that if x is equal to 0, dy by dx slope is equal to theta A, and if x is equal to L, slope dy by dx is equal to theta B. So these two boundary conditions can be used. So boundary conditions to be used to calculate C1 and C2, generally we use the deflection boundary condition. You can see here for this figure, at x is equal to 0, we have selected section xx in the last segment, so that x varies, the small x varies from 0 to L. Means when x is equal to 0 means at the origin displacement is 0, x is equal to 0, x is equal to 0, y is equal to 0. Again, if x is equal to L, then again displacement is 0, y is equal to 0. Two unknown values C1 and C2 and two boundary condition, we can easily solve for C1 and C2. So this is for the simply supported beam subjected to combination of load. The second category of beam, suppose a single overhanging beam subjected to combination of loads, say W1 and UDL, W2. So this is W per meter length. Say the distance is this is L1 and this is L2. Again, if you draw the deflection deflected curve, deflection will be like this. It will be like this. This is deflected beam. Here we select again section in the last segment, and this is point A and this is say B, C, D and E. Again we select section in the last segment so that x varies from 0 to L. So the total distance is equal to L. L1, L2, the total distance is L. When beam is simply supported, at the supports deflection is 0. We have written two boundary conditions. Boundary condition 1, again boundary condition 2. So, 2 conditions, 2 unknowns we can easily solve. We can also apply 2 boundary condition here based on this loading condition and the displacement position. You can see here again when x is equal to 0, displacement is 0. Here displacement is 0, here also displacement is 0. Then we can write one condition at x is equal to 0, then y is equal to displacement means deflection. Next, here what we did, x is equal to L, y is equal to 0, x is equal to L, y is equal to 0. But if you put x is equal to L, y is not is equal to 0 because there is a displacement. So, here y is equal to 0, where y is 0? At the support y is 0, displacement is 0. Then, second boundary condition is at x is equal to 0, y is 0. Next, at x is equal to, x varies from 0 to L, x is equal to L1, then y is equal to 0. Next, at x is equal to L1, y is equal to 0. So, these are the again 2 boundary conditions for this type of loading for a single overhanging beam. For example, third case, if the beam is again a single overhanging beam, overhanging to the is to the left hand side, overhanging is to the left hand side. Let the length of the beam is L. So, distance from the left hand side to the first support is L1 and distance from left support to right support is L2. Again here also we take section in the last segment. So, there are 3 segments here, A, B and call this as C. We select section in the last segment so that x varies from 0 to L. In previous cases x is equal to 0, y is equal to 0, here also x is equal to 0, y is equal to 0. Here again x is equal to x, here x we have selected section in the last segment so that x varies from 0 to L. If x is equal to 0, now if you consider this loading pattern like this, say W1, W2 or a load acting somewhere here, W3 something like that, the bending pattern of the beam will be beam will bend like this, like this. See here the displacement condition, displacement is 0 at displacement is 0 at L1 and displacement 0 at the end, means x is equal to 0, then y is not equal to 0, displacement is not 0. When then where is displacement 0? When x is equal to L1, y is equal to 0, then when x is equal to, we have to measure origin from here, x is equal to L1 plus L2, then y is equal to 0. So, boundary condition to be used here is number 1, at x is equal to L1 at the support, y is equal to 0. Similarly, at x is equal to L1 plus L2, x is equal to L1 plus L2, then y is equal to 0. So, these 2 boundary conditions to be used to find out constant C1 and C2. This is another combination of load. And the last combination of load is suppose if we come across the beam with the double overhang. Again, let the L1 is the total length of the beam. So L1 is, so L is the total length of the beam, L1 is the length from the origin to the first support, L2 between the support and L3 from right support to the end. We take support points as say A and B, combination of load is like this, W2, W1. So even without load also, W2 or W3, something like that, even without this load also the beam bend differently. So again here we take section in the last segment. Section in the last segment means if you remove this, see this is the section, and we mark x from the origin or from the starting point, so that x varies from 0 to L. And if you consider the deflection pattern, so beam will deflect like this. So deflection is 0 here, deflection is 0 here, means deflection 0 at the supports. Again here the boundary condition is, here x again x varies from 0 to L, x is equal to 0, y is not 0, x is equal to 0, where y is 0, x is equal to L1, y is equal to 0, and x is equal to L1 plus L2, y is equal to 0. Here at x is equal to L1, then y is equal to 0. Again at x is equal to, where again slope is 0, deflection is 0, x is equal to 0, here it is 0, x is equal to L1 plus L2, then y is equal to 0. So this is the combination of load which we come across. For this combination of loads, we can write the boundary condition, any span length, the magnitude of load it is. So this is the worst combination, all these 4 combination which we come across. Based on the loading pattern and the end condition and supporting position of the beam, we can write boundary conditions. One thing we can easily remember is that wherever we come across support, there deflection is 0. Wherever support is there, at the support there is no displacement, deflection is 0. If you understand that it is at the support, deflection is always 0, then you can easily write the boundary condition, apply the boundary condition. In a given beam, always if you select the section in the last segment, x always varies from 0 to L. For this type of condition, for simply supported beam, we have selected section in the last segment, x varies from 0 to L. So deflection is 0, displacement is 0 at point A and B, that's what it is, x is equal to 0, y is equal to 0. Then second condition is x is equal to L, y is equal to 0. Second case, it is for a single overhanging beam, deflection is 0 at A and B at the support point. So boundary condition at x is equal to 0, y is equal to 0, at x is equal to L1, y is equal to 0. If you substitute these boundary conditions in the last equation number 4 which we have written, you will get C1 and C2 automatically. Next, for overhang to the left hand side, again so C is the origin, x we have marked from origin to the up to the last segment. We have selected section in the last segment. Here also x varies from 0 to L. X is equal to 0, y is not 0, but x is equal to 0, x is equal to L1, y is 0, displacement is 0. Again x is equal to, here x is equal to L1 plus L2, then y is equal to 0, x is equal to L1 plus L2, y is equal to 0. The last combination of load beam pattern is double overhanging beam. Here again we have selected section in the last segment, so that x varies from 0 to L. X is equal to 0, y is not equal to 0, x is equal to 0, y is displacement is not 0, but x is equal to L1, displacement is 0. Similarly, x is equal to, what is this, L1 plus L2, then displacement is 0, x is equal to L1 plus L2, y is equal to 0. So these are the known boundary conditions for any given combination of loading. If you understand these boundary conditions along with the concept of Macaulay's method, and by using differential equation for deflected beam, we can solve any numerical problem. So before coming to next class, again go through these boundary conditions, understand this boundary condition, then we can take up the numerical problem in the next class.